is the 8th order system here. So if you have something like this, you can do a Routh table. You have to realize something like Routh criteria or Routh-Hurwitz criteria, you wouldn't think this would be very relevant in now, because something like this, you can use computers to figure out the roots, right? So why would you need Routh table? Why would you need Routh-Hurwitz criteria? If you find the roots, you'll know whether the roots are in the right or left half plane. So you would know. This is something to think about. Think about this. So you construct your Routh table S8 and you pre-populate the first two rows, right? You have 1, 10, 48, 128, and 128. Yeah, 128. Okay, and then you have 324, 96, 192. So what you can do here is, the first thing is you simplify this, 3, 1, 8, 3, 1, 3, sorry, 64, 42. Okay. All right, so your S6 now would be 10 minus 8, right? 2. This would be we have 8 into 84 minus 320 over 8. This is 32. Right. Let's do this. 128, 32. I have 2, 16, 5, 2 plus 8. Six, 9, 4096. So let me just write down these from here. So 2, 16, 64, 128. Say that again. Hmm? 8. 16. So do you see these? You see that, right? So what happens here is S5 would be 0, 0, 0, 0, 0. So you cannot proceed. Okay. So what you do is, in in such a case, this, so if you do this minus this over 8, you're going to get 16. Yeah. You do that over 8, right? So when you do this, what you're going to do, if you encounter such a case, what you're going to do is you're going to construct a polynomial in this, the row above 0. Okay? So the polynomial is S6 plus 8S4 plus 32S square plus 64. You see how I got this polynomial? I'm constructing this polynomial. Okay. P of S is this. So you have S6, S4, S2, S0. This one? Okay. You get 8? You have 384, 64 over 8 is 8. That's what you're saying? Right. So if that is 4, then it will be something different actually. One 8 32 64. 1 8 32 64. 64. This one? All right. For now, just we'll forget about the arithmetic. Assume there is a bunch of zeros. Okay. We'll do that and see how to address row of zeros. We'll talk about how to deal with the row of zeros. Right, yeah. So you have a row of zeros. So what you do is you do P of S and then you take the derivative of P of S with respect to S. This would be 6 S5 plus 32 S cube plus 64 S, right? Plus 0. So what you do is you replace these zeros with the coefficients of these. So you have 6, 32, 64, 0 and 0. Okay? So you have 3, 16, 32. Okay. And now you keep continuing your this thing. So S4 would be simply 24 minus 16, which is 8 over 3. Okay. So this would be 8 into 32 minus 16 into 32. So it is, so sorry, 16 into 32 minus 8 into 32, which is 32 into 8 over 16, which is 16. Okay. And this would be 64, 0, 0. So this is how you tackle the Routh-Hurwitz criteria when you encounter a row of zeros. Okay. Is this right? 16? No? So 32 into, sorry, 16 into, so 16 into 32 minus 8 into 32, which is 8 into 32, right? 8 into 32 over 16. 2, sorry, 8, 1, 2, 16, I think that's right. Right. Correct. Yeah. So if you'll be given one problem where you'll have to deal with one special case and figure out if the system is stable or not. Okay. All right. You have 3, 16, 3, 16, 32. So whichever row is 0, the row above that. Right. Yeah. So what you're going to end up with, coefficients for S5, right? The polynomial S5, and that is what you need to substitute. Okay. All right. We'll stop it here. So this wraps up stability. Okay. Next chapter will discuss about steady state error, and that is your next exam will cover the block diagram reduction, stability, and steady state error. All right. Your exams, midterm exam. Midterm exam actually was really easy. It didn't really
get started. So, as I told you in the last class, we're going to go into a new chapter. This is steady state error.
So this would be what's on the last test? We'll cover that. So not the next test.
This will be on the next test.
Chapter 6 and 7.
Chapter 5, 6, 7.
5, 6, and 7. It's gonna be
5 is, see, everything is right, block diagram and Mason's rule. Block diagram is something you have to work on. Mason's rule is very straightforward. Stability, again, it's just Routh-Hurwitz criteria. There are three things. The Routh table itself, you have a 0 in the column, first column, and a whole bunch of a 0 row. Those are three cases, which is chapter 6. There is not much, it's just one section or two sections. And the steady state error, you don't want to see this only in the final exam. You will just be overwhelmed. So steady state error is defined So we have been talking about system response, right? And we often used this. So you have, this is the C of S. This is time t. Okay. And this is B. Right. So system response itself, as we discussed, can be divided into transient response and steady state. So you can say this is the transient region. This is the transient response. And this part is steady state response. So when we are talking about steady state response, the most important characteristic of steady state response is the steady state error. And this is what your steady state error is defined. So it's the difference between the input signal and the output signal after it reaches steady state. Okay. So this is, you can say, it reaches steady state at this point, and that error, steady state error, is the difference between the input, whatever is being tracked, and what the actual output is. Your desired, for example, the desired output is this dotted line. This is what you desire. But your actual output or actual response is off by a certain amount. That is your steady state response.
Now, when we talk about steady state response, we talk about steady state response in terms of unity, feedback. So you have your GFS.
This is a unity feedback system because what is being fed back is just the output signal. Here, the T of S is simply T of S. If you look at this, can you apply this concept to this figure? What is the error signal? And we have talked about this error signal in the past. Where is this error signal?
Right after the summing zone.
Right after the summing zone. So this is your error signal, right? So error signal is essentially R of S minus C of S. And so your steady state error E of S is this, but C of S is defined as E of S into G of S, correct? Therefore, E of S is equal to R of S minus E of S into G of S. And if you take it on the other side, E of S should be E of S into 1 plus G of S is equal to R. Or E of S is R of S. By definition, this is how you define, or this is the notation used for steady state error, is limit as t tends to infinity.
Does this make sense?
So think about this. This is your E of S, right? E of S is the error signal expressed in terms of the frequency variable or the Laplace variable, right? If you want E of t, you're going to just take the inverse Laplace, right? You're going to get this E of t, alright? E of t is the error. Steady state error is just defined as E of t as t tends to infinity, right? So if you look at when t goes to infinity, what is the error? That is your steady state.
Easy enough. So it is represented by E of infinity equal to limit t
Tends to infinity. As t tends to infinity of E of t. It's just a function of time. Function of time as time tends to infinity. Okay. By definition.
So if you this becomes limit as s tends to 0 s e.
Okay. This is how steady state error is expressed in terms of the Laplace transform of the error. So these two are equivalent definition.
Now if you apply this line definition to say E infinity is equal to limit as s tends to 0
This is the definition of steady state error in terms of G of S. Okay. Now, here, understand that why we are expressing this in terms, why we are trying to express this in terms of G of S. Okay. So any system can be expressed as a unity feedback system. Okay. Even if you're given something like this, so for example, from the last lab, you had this, right? You had H of this. So this is not a unity feedback system, correct? No. Because there is H of S is getting multiplied by H of S, but you can express this as a unity feedback system. And that's when it becomes fairly simple to adopt this particular definition of steady state. Okay. We'll look at how to convert non-unity feedback systems to unity feedback systems and apply the steady state error. Similarly, E infinity can also be expressed as look at what is T of this. T of this is simply T of this
R of S. Okay. You check this definition. T of S is this, right? This is also equal to T of S. This is how T of S is defined. Okay. T of S is the closed loop transfer function. G of S is the open loop transfer function. So T of S is that. Right? So therefore, C of S would be T of S into R of S. But what is R of S? E of S minus C of S, or plus C of S. One minus E of S. Okay. E of S or E of S is equal to this is the definition expressed in terms of closed loop transfer function T. These are the two definitions you can use. Can I erase this? No?
Let me get this. You said that's the representation of it in
T of S. Closed loop transfer function T of S. For step input, we'll be using this definition for step input, what is the steady state error? How do we define it? Quite simply, it is. Here, step input means R of S is simply 1 over S, right? So you have limit as S tends to 0, S into 1 over S divided by 1 plus this cancel. E infinity can be expressed as, so here we'll do this. We'll use this step. 1 over 1 plus limit S tends to 0. Okay. Similarly, E ramp is equal to limit as S tends to 0, S into 1 over S square. And then simply 1 over limit S tends to 0. So think about this. What happens here? You have this becomes 1 over S plus S G of S, right? And you have the limit as it stays. So what happens to this term? It simply goes to 0, right? Because S goes to 0, this goes to 0. That's the reason you get just limit of S tends to 0, S into G.
For the ramp,
For the ramp steady state here, is that 1 over Sx, the x power? Is that x for the ramp?
There's no X.
Is that S squared?
S square. This one?
Oh, that's S squared.
Yeah. For what is R of S for ramp?
1 over S squared.
See, all you're doing is substituting this for, when you want to define specific steady state error, you're defining it for specific input signal. What does ramp mean? It's for the input signal, ramp input. So that R of S is 1 over S square. That's it. Keep in mind that if you remember this definition and you understand what R of S is, you can arrive at any other definition. Okay? It's not, you don't have to memorize this one. You really don't. It can take like 15 to 30 seconds for you to get to that. Not more than that. take a look at an example. You'll be given something like this, and this is your example. You just find one E step, E ramp, so your E infinity, already defined E infinity, limit as s tends to 0, s r of s over 1, right? So what is GS here? G of s?
That whole thing with all the block.
This whole thing, right? So you just apply that E step is equal to limit and s tends to 0, s into 1 over s, 1 plus 120 s plus 2 over s plus 3 into s plus 2. So this cancels. We can use this definition directly, but I'm just showing you how you can do it from a more fundamental definition. All you need to do is substitute s equal to 0. That's it. So here, this would be, if you substitute s equal to 0, what are you going to get? 1 over 1 plus 120 into 2 divided by 3 into 4. You see it? You substitute s equal to 0. 0, 0, 0. There is no s in the numerator. This would be 1, this is 3, 12, 10. You have 1 over 21. So E infinity step is simply 1 over 21.
Where you have E infinity ramp and E infinity parabolic, in the denominator, they're not a 1 plus the limit as s approaches 0.
That's what I showed you here. You have s in the numerator, right? Sorry, s in the numerator and 1 over s squared. Okay? So this square s cancels.
Yeah, I see that.
So s comes to the denominator. S plus 0. What happens if you apply s, if you make s equal to 0? This goes to 0, right?
Okay.
So the limit only applies to this term. This is an example in book. It's example. Example 7.2, page 347. So what is E ramp? Can you do it yourself? You tell me what E ramp is, or the steady state error for ramp input. Right, what is the value?
Once we eliminate all the S's.
Yeah, tell me the value.
Well, we're limited S, what's 0 times this.
Huh? Tell me the value. Do it and tell me the value.
It would be 1 over 21x.
Huh?
What would be 1 over 21x?
S will not be there. That's what I'm trying to tell you. Do it.
Right.
Because we are substituting S equal to 0. That's what we are doing.
Oh, so it would be 1 over 20.
Hmm?
No, it's only 2,000.
Guys, do it. Everybody do it. You should be able to do this.
1 over 20.
Hmm?
Maybe 1 over 20. If you, no, it's 0. Multiply by the S. 0, you gotta multiply by S. So it's gonna be 1 less than S. Where you can't divide by 0 yet.
Hmm?
You can't divide by 0. But 0. Please, it's another way.
Hmm? Why negative? It's infinity. You don't confuse with undefined and infinity. Okay? 1 over 0 is undefined. Infinity over infinity is undefined. 1 over infinity, 1 over 0 is defined. 1 over infinity is 0, 1 over 0 is infinity. Okay? This is actually infinity. Okay? So if you do, what does this mean? If you actually supply a ramp input to that particular system,
It's gonna always keep track.
it's going to diverge, you know, if this is what it is supposed to track, the output is going to keep diverging away from the steady state error, right? So steady state error, this is how the steady state error is defined for ramp input, correct? Ramp input is, so this is going to keep on increasing, and it's potentially going to go to infinity. So the system is not stable for ramp input. That's what it is. What is E parabolic? It is infinity again. So we'll look at one more example just to give. I want to make a point. This will lead into the next discussion for next class. We looked at an example. Look at another example. here E step infinity will be what? Limit of distance to 0. 1 over 1 plus G. Right? That's okay. Or you can take it like this. So this would be what? 1 over 1 plus 100 into 2 into 6 over 0 into 3 into 4. So what is this? Huh?
So what? It's 1. Oh, it's 0. Solo answer is going to be 1.
This goes to infinity. Okay?
1 plus infinity is
So this is 1 over infinity, which is 0. And E ran is simply limit 1 over S into G, right? So here it is 1 over 100 into 2 into 6. See, what happens is this S cancels with this S. When you substitute G of S here, it cancels with this S.
But isn't ramp 1 over S?
Huh?
I said, isn't ramp 1 over S over SGS? Like, I mean.
We did all of that. So this is, after doing all of that, this is the specific
That's what
definition.
you get left.
So you have, so this is 3, 1 over 100, right? And E is simply infinity. You can substitute. So it's going to be S square into G of S, right? Which means one of the S is going to cancel, but there's going to be a S. When that becomes 0, it will be 1 over 0, which is infinity. There is a specific pattern here, and that is what I want to get you guys to look at this and look at this. Okay? This has a pure integrator term or a pure S term in the denominator. Do you see it?
Yes.
There is no S term in the denominator here. So this 1 over S term, it's called the pure integrator.
So that would cause you to have a real number for each pure integrator.
Right. If there is no pure integrator, the steady state error for the step input only is finite. The steady state error for ramp and parabola is infinite. No integrator term. If there is one integrator term, just one, that means 1 over S. The steady state error for step input is 0. The steady state error for ramp input is finite. And the steady state error for a parabolic input is
infinity. And there will be one more case where it will be s squared. 1 over s squared. That is 2 pure integrated. So in that case, this will be 0, this will be 0, this will be finite. Okay? So the pattern is finite, infinity, infinity, 0, finite, infinity, 0, 0, finite. These are the 3 cases which you need to remember. And you can arrive at those cases by yourself without much trouble or without much effort. This is section 7.2, and we'll extend this discussion, which is in the next class. That is section 7.3.